Hi everyone, welcome to this video about solid-state characterization techniques. In this occasion, we are going to dive into thermogravimetric analysis or TGA. What is this technique and why is it important for drug development? Well, each substance has a specific thermal behavior. The phase changes that a substance undergoes, from solid to liquid and liquid to gas, for instance, always involve the absorption or release of energy, normally heat. In other words, every phase change happens at a specific temperature, which is characteristic of that substance under certain conditions. One possible phase change in an active substance or a drug is the crystallization. Crystallization is the process where a substance transitions from a liquid or gaseous state into a solid form with a highly ordered, repeating arrangement of atoms or molecules, known as crystal. Depending on the environmental conditions, temperature, pressure, solvents, impurities, etc., different crystalline modifications can be obtained. Substance able to adapt different crystalline forms is said to exhibit polymorphism, which is important in pharmacy because it can affect the solubility and permeability of the substance, significantly impacting its bioavailability. The most famous example of polymorphism is carbon, graphite, and diamond. The importance of polymorphism in pharmacy is such that several chapters of the Aulton's book are dedicated to this property. Another important step of drug thermal behavior is degradation. High temperatures accelerate oxidation, reduction, and hydrolysis reaction, which lead to drug degradation. Knowing the temperature of this event is also important for the development of drug delivery systems, especially if high temperature steps are needed. For instance, we won't be able to sterilize by heat a substance that degrades at temperatures lower than 120 degrees centigrade. So all the thermal properties of a substance are a good piece of information during drug characterization, drug development, and medicine formulation. The thermal properties of a substance can be measured in several ways, one of which is thermogravimetric analysis or TGA. This technique measures the mass loss of a substance due to the influence of temperature. So, TGA is a method in which changes in physical and chemical properties of materials are measured as a function of increasing temperature or as a function of time. In TGA, the sample is continually weighted while heating, as a certain gas atmosphere is passed over it. This gas could contain oxygen or could be an inert gas atmosphere such as nitrogen. During this analysis, the sample can undergo solvent evaporation, such as water, melting or fusion if crystals were present, crystallization, decomposition, and so on. Some of these changes are associated with changes in sample mass, for example, water evaporation or decomposition. If that's the case, changes in the mass will be detected and plotted, while others only imply a heat transfer enthalpy without modifying the sample mass, such as melting point or crystallization, for instance. In the latter case, no signs will be detected during TGA, and complementary thermal techniques, such as differential scanning calorimetry or DSC, may be needed. In other words, TGA only reveals changes associated with variation in sample weight. In TGA, three variations are commonly employed: dynamic TGA, static TGA, or quasi-static TGA. In dynamic measurements, the temperature continues to increase over time as mass is recorded. This allows simultaneous identification of how much sample is lost and the temperature at which it occurs. In static TGA, the temperature is held constant as the mass is measured. This can be used to gain more information on a decomposition that happens at a certain temperature, or to investigate a material's ability to withstand a given temperature. For quasi-static TGA, the sample is heated in multiple temperature intervals and held at those intervals for a time, often until the mass stabilizes. This is ideal for investigating substances that are known to decompose in various ways at different temperatures, and better characterizing the way in which they decompose.
This technique is much more complex, and more in-depth information must be acquired before designing a TGA experiment using TGA instrument or reading the results. As preliminary information, factors such as surface area of the sample, instrument, type and composition of the atmosphere used, crucible material, shape and size, temperature run rate, sample mass, volume or morphology are to be considered when designing an experiment and/or interpreting the results, since they can modify the temperature or rate of the thermal events. In the description box down below you can find some links and further literature references about this technique and variables to be considered. Let's see now what a TGA equipment looks like. Different fabricants provide TGA devices with different aspects and spatial configurations. These are just some examples. In any case, every thermogravimetric analyzer, TGA equipment or thermobalance consists of several basic components, including a balance, a furnace, programmed temperature control system, and recording system. In the following scheme, we can identify the sample pan or crucible. The sample to be analyzed is placed in a small pan or crucible, usually made of ceramic or inert metal. A balance system, a high-precision balance often capable of detecting microgram or even nanogram mass changes, is connected to the sample pan. It continuously measures the sample's weight throughout the experiment. The furnace provides a controlled heating or cooling environment for the sample. It's capable of reaching high temperatures, often up to 1000 degrees or higher. And finally, the gas supply. A gas supply system is used to introduce a purge gas, like nitrogen or hot oxygen, into the furnace to control the atmosphere around the sample. In terms of results, we expect to obtain a TG curve where sample mass is plotted in the y-axis and temperature or time are on the x-axis. The shape of the curve A represents a thermally stable sample. B is normally due to desorption or drying. The composition usually has the shape of curves C for a simple one, or curves D and E when different decomposition steps are happening. The heating rate can affect the shape, see curve E, which can also be due to the absence of intermediaries of the substance in the composition. Increases in sample mass are also possible for certain type of chemical reactions, such as surface oxidation, as it happens for curves F and G. This is another example of a TG curve of an unknown substance, see the green line, obtained from the website on screen. This curve shows two early mass loss events before 100 degrees, usually associated with water evaporation. The blue line, secondary y-axis, represents the heat flow, that is, the exchanges or absorption of heat during the experiment. Endothermal events, heat absorption, have a downward blue shape, while heat emission, exothermal events, have the opposite shape. Water evaporation requires energy, being an exothermal event. Other events, such as oxidation, typically known as burning, release energy, and so an exothermic event can be observed. Now let's look at some real examples of a TG curve and try to read them. The type of events expected from a TGA analysis not only depend on the analytical conditions but also on the type of sample. Let's start with an easy one, the TGA of calcium oxalate. Calcium oxalate monohydrate decomposing calcium oxalate by evaporation of water around 100 degrees followed by a new chemical reaction at approximately 500 from calcium oxalate to calcium carbonate. As it is well known, calcium carbonate then transforms into calcium oxide in a third step between 6 and 700.
In this article, the antiparasitic drug Praziquantel was loaded into two types of clays, sepiolite and mommorionite, which are natural inorganic platforms. The TGA of these interaction products was very simple. Pure drug experimented a one-step mass loss event starting around 200 degrees centigrade with almost full mass disappearance at approximately 350. This is typical for organic compounds. They usually undergo thermal decomposition at a certain temperature. Red lines correspond to clays, which are inorganic materials with excellent thermal resistance. The TGA curve of both clays are constituted by an early mass loss, approximately 10% mass, before 100 degrees, usually associated with water. This happens for both sepiolite and mommorionite. Clays also undergo dehydroxylation, but this event is not visible here because the analysis stopped at 400 degrees, so the mass maintained a constant value from 100 to 400, indicating no further chemical reactions in both materials due to heat. The loading of Praziquantel with both clays can be justified by the weight loss around 300, which corresponds to the drug and not the clay. See how the red line does not show any change at that temperature. This was visible for mommorionite and also sepiolite. The third example shows how TGA can be used to determine the amount of drug loaded or carried by another inorganic platform. In this study, researchers developed a TGA method to measure the loading of indapamide in mesoporous silica nanoparticles. As it happens for a major part of drug, indapamide decomposed almost completely at a certain temperature. In this case, indapamide decomposition happens in a two-step process. After drug loading, the weight loss step appears in the same region as indapamide, indicating its degradation after being loaded in the silica particles. By subtracting the differential weight loss between the curves and knowing the percentage lost by the pure drug, it is possible to discern the amount of drug effectively loaded, as shown by the percentages in the figure. That concludes our introduction to thermogravimetric analysis. I hope this video has provided you with a simple but clear picture of how TGA works and why it's such a valuable technique for studying material behavior. Don't forget though that this is just the beginning. Keep exploring, keep questioning, and join us the next time as we dive deeper into other applications. Thanks for watching.